which means partner quiz coming up fairly soon and unit test. Okay, probably not next week though. Not next week.
Like, do you know when it is?
The week after, some point, perhaps, maybe towards the end. This last section is going to take us a little bit to go over because it's something new to us. I mean, all of this has been new, but this is kind of an important topic for us that's going to lead us into the next unit. So we're going to spend some time on it. This section is titled Improper Integrals. So the integrals that you guys have been doing so far in either Calc 1 or in this class have always looked like the integral from a to b, like a number to a number. Improper integrals, we're going to start to get a little feisty, and we're going to throw in some infinities, maybe as a lower bound, an upper bound, or maybe even both bounds. Okay, so improper integrals is essentially involving some type of an infinity as a bound. So we're going to investigate that in this section. The chart on page 83 might look a little familiar to you guys because we did something like this a little bit last year. To help us with these improper integrals, we're going to start to analyze growth rates of functions, like what types of functions grow faster or slower than other ones. So we're going to, and maybe you might remember growth rates, like which functions grow faster than others, but we're going to investigate this idea using a calculator. Okay. So in the second column, we have a bunch of different functions, and we're going to plug in some different x values. Notice how they're getting bigger and bigger and bigger, okay, signifying how we're going off towards infinity. And once we have all of these function values, we're going to go ahead and rank these functions from slowest to fastest in terms of their growth rates. So some of these you might be able to do in your heads. Other ones you might have to use your calculator. For instance, if you were to plug 1 into the x function, you'd get 1. If you'd plug in 10, you'd get 10. Plug in 100, you get 100. Plug in 1,000, you get 1,000. If you tried to plug in 1 into a constant function of 5, you'd only ever get out 5. Same thing with the 10 and the 100 and the 1,000. So what I want you guys to do is take the time to fill out that chart with your calculator, either doing one thing at a time or maybe utilizing some different characteristics of your calculator, like the table function or things like that. We might have to be able to type in this guy, x exclamation point. Have you seen that before? We only saw it last year when we did this example, and that was basically it. But we're going to see that exclamation point much more this year. Do we know what that even is? Yeah. It's called a factorial. Okay, so I'm going to go ahead and erase this. Okay, it's not necessarily a very excited X. I know it's an exclamation point, but that doesn't mean it's excited. Do you know how factorials work? For instance, if you plugged in 10, you'd have 10 factorial. What does that actually mean? Yeah.
Isn't that 10 times 9 times 3, and then it just continues on?
All the way down to 1, exactly. Okay, so there is a factorial button on your calculator, so you don't have to actually sit there and type in all of that, because plugging in 1,000 would take you forever. So on your calculator, if you hit the math button and scroll over to probability, okay, the PRB option at the very end, you see the exclamation point for number 4, okay? So you type in 10 and then go to that probability menu and select the exclamation point, and you get that number. So that's what I want you to write down in that little box in the chart. Now some of these are going to eventually get so large that your calculator cannot handle it. You might get an overflow value. Some of them might be written in scientific notation. You might see a little e and then a number after that. That's like times 10 to a power. So you might have to write those down in the boxes as well. Okay, so take the time to go ahead and fill out those values. I'll do them up here as well, so you can kind of check your work as you go. Can we get those values? Seem to check out? We got them? Okay. So taking a look at the chart, let's go ahead and try to rank these functions slowest to fastest. So if you think about growth rates, the larger the x's you have, like the further you travel to the right on a graph, if you're growing fairly slowly, your y values, aka heights, shouldn't be that large. And all of these values you filled out in the table are y values. Okay, those are outputs. So as you go to the right towards infinity, which one seems to be the smallest in terms of its height, aka the slowest growing? Yeah. 5. Yep. Okay, that's the smallest height. So we'll rank them slowest to fastest. We'll say this is number 1. So then our next slowest, what's a little bit higher than 5 based off our values? The natural log, yep. Okay. And then again, based off the values, what's the next highest one after 6.9? Just x. Okay, that's a big jump, right? We go from 6.9 to 1,000, but it's still the next highest. What about the next one? X squared, yep. X cubed, yep. So we go from 1,000 to 1,000,000 to 1,000,000,000. Next one? X to the 10th, okay? And then it looks like after that we kind of hit the stage where the calculator couldn't handle it. Okay, so we know that these are the next fastest growing ones, but unfortunately at the x value of 1,000, that's not really telling us which one is growing faster or slower. So instead of looking in the 1,000 column, let's go ahead and move to the 100 column to perhaps help us. So take a look at these numbers, and then which one is the slowest growing from those, aka the smaller height. Yeah, 2 to the x. Okay, and then looks like e to the x, and then 4 to the x. Okay, once you get into scientific notation, you got to look at the power on the 10 more than the actual multiplier number out front. Okay, and then after that we have the errors, which were too big, so then we'll move to the next or the previous column to help us out there. Looks like x factorial is 10. And the fastest growing function is x to the x. Does that make sense how we can read the table that way? Okay, so based off this ranking, let's go ahead and try to classify these functions based off their type. For instance, if I said a power function, like x to a power, is that faster or slower growing than a log function? Maybe exponential can be compared to factorial. So these are different functions, but we can classify them based off their types. So we said the slowest one was 5, but how might you classify the function 5? By what name is that function? If it's just a number, it's considered constant. Okay, so constant is the slowest growing function. After that, we said the natural log was the next slowest. And then after that, we got into x, x squared, x cubed, x to the 10th. So all of those kind of have the same format. Those are what are called power functions, where you have x to a power. More typically known as polynomials. All right, so then after those, we had 7, 8, and 9, which kind of all looked the same. 2 to the x, e to the x, 4 to the x. How can we classify those functions? By what name? Exponential. So that is kind of considered a base to a variable power. Okay, exponential functions. After that, we had the factorial, and after that, we had x to the x. Okay, so in terms of slowest to fastest, we can classify functions in that method. But notice how, for instance, if I were comparing an exponential to a natural log, I know which one is growing faster. But how might you compare a power function to a power function? If you had two different power functions, how could you tell which one's growing faster? For instance, if you look at all of those options at the top. How can you tell which power function is growing faster if you're comparing two different ones? Yeah. By the power. Okay. What if you were comparing two exponential functions to each other? If you look at those ones, how can you tell which one's growing faster than the other? The base, right? Okay. We said that the 4 to the x was growing faster than e to the x. E is 2.718, so since that base is smaller, that one's growing slower. Okay, so if you're comparing different functions, we can use this progression, but if you're comparing the same function, you may have to look a little bit more deeper into that. For instance, the power value or the base value. So what we're going to focus on in this section is taking a look at the growth rates, which one's growing faster than the other. So let's go ahead and think about, we're going to go back to limits just for a second. Okay, not much. So based off of this table, if the x's were to approach infinity, okay, as the x's get larger and larger, what if you were comparing a slow growing function to a fast growing function? Okay, in terms of division, like a ratio, a comparison. If you were to take something slow divided by something fast, in other words, if you think about the numbers, something small divided by something huge, what do you think you'd be getting closer to? A limit idea. You're getting closer and closer to 0. Okay. Graphically speaking, this is a horizontal asymptote. Okay, if the further you go to the right on the graph, this is your height. Okay, you're approaching a horizontal asymptote. What if you were to compare a fast to a slow, kind of reciprocate it? If you had something large divided by something small, yeah? Infinity, okay. It could be positive or negative. So graphically speaking, you might be going up, you could be going down. It depends on the signs of the functions. All right, this one's a little tricky. What if you had the same function divided by the same function? Like they had the same growth rate, like x to the third divided by an x to the third, or a 2x divided by 2x. They have the exact same growth rate. Yeah.
1.
It could be 1. Okay. What if I had like 2x to the third over 4x to the third? It'd be 1/2. Okay. You would take the ratio of those coefficients. I'm not sure if these are coming back to us a little bit in terms of horizontal asymptotes or not. So I'm running out of room, but I'm going to say ratio of coefficients. Okay, that's just if you have the same growth rate, not the same type of function. Okay, the same growth rate. Perfect. Okay, so we're going to reference this chart throughout the unit in terms of the slow and fast idea and comparing. So we really have to be familiar with that progression. Okay, slowest growing to fastest growing. We're going to have to identify those fairly quickly. All right, so let's get into these kind of improper integrals where we have one of the bounds or maybe both of the bounds going towards infinity. I want you to take the time on your calculator to plug in those 3 different examples. Let your calculator do the work, and I want you to write down the result. Yeah.
I have an appointment at 11, so can I leave around like 50?
That's fine. Yeah.
It's pretty much done.
Right, just a little bit before, but that's okay. Can we get those numbers? 4.6, 6.9, 13.8, roughly? Okay. I also forgot to mention in terms of the limits that we were discussing before, this ratio of your coefficients, like 1 or 1/2, that's also a horizontal asymptote. Okay, the further you go to the right, this is where your graph would level off because it's a numbered value. Okay? So back to these. Notice how we're going from 1 to 100, 1 to 1,000, 1 to 1,000,000. What if we were to change it from 1 to infinity? Because you can't really type in infinity on your calculator. Can we get an idea about what this might be? Yeah. Positive infinity. Notice how, remember, integral essentially means area. Okay, so the area under this graph from 1 to 100 is this amount, and then from 1 to 1,000 is that amount, 1 to 1,000,000 is that amount. So notice how as we keep increasing the x value towards infinity, the area value seems to increase as well without bound. So you're just going to keep going forever towards infinity. I want you to try the same thing for the bottom 2, though. We're going to change up the function a little bit, take a look at an exponential. Go ahead and type those in. right, so based off those two, what do you think the area under that graph would be from 1 to infinity? Infinity like last time? No, probably not. Probably the 0.368. We doing okay?
Whenever, I
Yeah.
just like tried typing in like 1 million like up above and
Yeah.
I got 0.
Did you really? Let me see.
Yeah, I don't know if maybe I typed it in wrong.
You did 1 million?
Yeah. Just because like I didn't see that we weren't supposed to type it in, but. Yeah.
Oh, that might be why. Your integral is from 1 to that. Did you do 1? I did 0 by accident.
I did 1 to 1 million and then still got 0.
You did?
Yeah.
Well, gee willikers, okay. Maybe we didn't go out far enough. I'll have to double check that. Okay. So, well, I guess what this is saying is based off of these two, what do you think it would be? But if you had to check more, okay, it might be a little bit more accurate to keep going. I'll double check that though. Okay. Thanks for bringing that up. All right. So, notice how in these two examples, we technically had one integral value in terms of its area that would approach infinity. So there's an infinite amount of area, okay, underneath this graph. However, if you take a look at the next one, we had a specific or finite amount of area underneath the graph. This is why 0 is kind of questioning me, because if you take a look at a graph, there should be some area underneath it, right? The 0 is kind of what's throwing me off, okay? But notice how we can have different results, okay? And if you think about it, this is what's a little weird. If you were to go from 1 to infinity, okay, like you're never ever ending, how could you have a finite amount of area? If your interval's never ending, how could your area end?
That's weird.
Isn't it? Okay, so we're going to investigate this.
Is it maybe our calculator's just not being smart enough?
No, it is. It is. Can we think about it? How can you have an infinite interval but a finite area? What would the graph look like? Can you think about it? If you had an infinite interval but a finite area.
It would be like a horizontal line that the area under the graph isn't changing at all.
Okay, so we're actually going to draw these on the next page, but this is what's leading us into this. So graphically speaking, it would have to look something like that, because, okay, you're going to have an infinite amount of area, but notice how the further you go off to the right, isn't the amount of area getting smaller and smaller and smaller and smaller? So if you keep adding the smaller and smaller and smaller and smaller area, maybe you are approaching some actual number, like this one in this case. Does that make sense? Kind of? Okay, so we're going to investigate that on the next page. All right, so we're going to sketch the graphs of these two functions, 1 over x and e to the negative x, and they should look something like this, but we're going to discuss the graphs a little bit further. So on your calculator, go ahead and type those in. Let's see, in terms of our, oh, can't see that. In terms of our window, maybe we'll go from 0 to 10, counting by ones. And 0 to 10 for the y's. We can always change it, okay? But if the integral is going from 1 to infinity, we realize that's really only in the first quadrant, right? We We don't have to worry about negative values for the x's or y's. Alright, so that's what we get. We have a ton of empty space in there, so maybe we'll kind of chop off some of that height. Instead of going all the way up to 10, I don't know, maybe we'll do 3. That's a little bit better. Okay, so we'll just draw a rough sketch of that in our notes. Let's see, I think the top function was 1 over x, and then the bottom function was the e to the negative x. Okay, so those are the graphs. It also wants us to kind of sketch or shade the region, the area that we're trying to figure out with this integral. So they're both going from 1 to infinity. So we'll just draw in kind of an understood x location of 1. And we're going to shade the area underneath those graphs towards infinity. So notice how underneath the e to the negative x, we would shade all of that area. And then for the 1 over x, we'd have all of that. Okay, so notice how both of those graphs kind of fit the graph I drew on the board, okay? But there's something different about them. There has to be, because they're both yielding a different result. The 1 over x had an infinite area, whereas the e to the negative x had a finite, okay? It had a specific numbered value. So what do you think is going on with these two graphs? Can you think about what's happening based off the picture? They look similar, but can you think about it? Maybe think about growth rates. We have 1 over x versus, let's see, a negative power. We can move that to the bottom, right? It would look like that, 1 over e to the x. Which one grows faster, x or e to the x? E to the x, that's an exponential, whereas x is considered a power function, okay? Its power is 1. So growth rates, if this one's growing faster, if it was just e to the x, notice how if you do 1 over that, that would mean it would be decreasing faster. Okay, if you trace it from left to right, you're going down. So it's something about the speed or the rate at which it's decreasing in this case. Okay, notice how e or e to the negative x is probably decreasing so quickly that the area out here is insignificant. Okay, it's so small that if you keep adding it, you're not going to be changing the integral or area value. Does that make sense? Kind of like what we discussed over here. Okay, but since x to the first grows slower than this one, okay, it's the way or manner in which it is decreasing is significant, because in terms of its area out here, when you add those amounts, you are affecting the area value. Wouldn't that make it go towards infinity? If you keep adding a significant number, isn't that number going to keep changing? Okay, so it's all about kind of this growth rate. What functions are you comparing? So we'll go ahead and write something down to that effect. E to the x, or negative x, is decreasing in a way that the area under the curve towards x approaching infinity is insignificant. Okay, there's still area out there. There must be, because you have an infinite interval. But the area that is out there is so small that if you keep adding it on, you're not going to change the area value. Okay, but that's not really the case for the other one. 1 over x is decreasing in a way that the area under the curve towards x approaching infinity is significant. Okay, if you were to keep adding on the area towards infinity, your total area value would be changing, getting larger. A little weird, wouldn't you think? Okay, it all depends on that growth rate. Do you notice, however, though, that both of them have a horizontal asymptote of 0? As you go out to the right, don't they both get closer and closer to 0? So we're not necessarily looking at the horizontal asymptote. It's more about the growth rate. Okay? We're going to stop there for today, and we'll take a look at growth rates a little bit further in terms of those power functions tomorrow.